Hi, I'm Geoffrey Litt, a PhD student at MIT CSAIL, and this is joint work done with Peter van Hardenberg and Orion Henry at the Ink and Switch Research Lab. Our work deals with the problem of evolving schemas over time, which is a pervasive problem in all sorts of systems, but is particularly interesting and challenging in the context of decentralized ones. Let me show you what I mean. So last year at this workshop, Peter and Martin Klettmann presented Pushpin, which is an architecture for building peer-to-peer collaborative applications in a local-first way. And what this means is that each user runs a local desktop application which can freely edit a local replica of some data, even when offline. And then when network is available, the peers can sync their edits with each other so they can collaborate on that data. Now, the data is stored in AutoMerge, which is a library that exposes a JSON document as a CRDT. And what this guarantees is that once two peers have synchronized all their edits, they will converge on seeing the same state. There's a lot of nice things about this programming model, but there is a tricky challenge that emerges pretty frequently in practice, which is what do we do when we want to change the shape of this JSON document? So for example, what if we want to rename this field called title to be called name? Now, we don't have a centralized system, so we can't necessarily force all of these users to simultaneously upgrade their software to accommodate this new schema. At the same time, we would like to maintain the ability for them to collaborate. So ideally, they can keep collaborating even as they're using these different versions of the software. It's not immediately obvious how this should work though. If this new client writes to this new property and the old clients expect data to be present in the old property, how can we work across that? One thing we could do is add compatibility shim code throughout our app. So for example, when we load from a field, we could have a fallback that looks in another field that might have been the old name for that field. The problem is this is very error prone, and this tends to also make it harder to reason about what the core application logic is doing. What would be better is to have some kind of principled schema transformation layer, where from the application perspective, we could just program against a single current data schema with strong guarantees, but we could somehow maintain this ability for these different peers to collaborate on the same data through the perspective of multiple data schemas. And this layer is exactly what we've built with our system called Cambria. In our system, developers specify translations between schemas using something called bidirectional lenses, which are a mechanism for writing a single data translation that can be executed in both a forward and backwards direction. Furthermore, these lenses get composed into a graph, which just lets us connect many schemas together in various ways. Then, using this graph of lenses, Cambria provides a number of useful things. First, it automatically translates data on the fly at runtime between schemas, which enables different peers to edit shared data across those schemas. Second, it produces static type definitions for each of these schemas, making it easy for developers to program with confidence against a particular schema. And finally, all of this is integrated with the AutoMerge CRDT, which means that we're able to preserve those eventual consistency properties we have in the Pushpin architecture, for example, while also enabling editing across schemas. Now, I know this is a bit abstract, so next I'm going to show you some demos of how we were able to use Cambria in a real sample application that we built, and then after that I'll circle back around and fill in more details. As a demo app, we built a decentralized issue tracker using the Pushpin architecture, and our goal was that we could evolve the application, add features, change the data schema, but throughout that maintain the ability for any two versions of the application to collaborate with each other on some shared data. Let me show you some examples of real changes that we made to the application. So on the left here, we have a very simple JSON document representing a task. It just has a name. And one thing we decided was that we wanted to add an array of tags to every task. Now in the middle here, you can see a short lens program written in our YAML syntax that expresses this change we'd like to make to the schema. We want to add a property called tags that's an array of strings. We can also see here what happens when we pass this concrete data through that lens. You'll notice we get a tags property, and it also has an empty array as the value because our lens language fills in a default value of empty array. Now, in some sense, this is a trivial transformation, but it's actually quite useful. So in our app, we might have some code that looks like this, that loads a document and adds a new tag. And without a layer like Cambria, we have to write a lot of guard code around that to make sure that it doesn't cause an exception. Things like checking that the property exists and making sure that it's an array. But if we've loaded the data through Cambria and we know that it conforms to our schema, then we can get rid of that code and return to just that one simple line. Next, let's look at a slightly more sophisticated example. We started out with each task having a complete property with a boolean marking whether it was done. But we decided we wanted to move to a status field that would track 3 possible values, to do, in progress, or done. So we can write a lens to do that. First, we just rename the field, and then we actually perform a conversion on the value itself. So here we've just specified a hard-coded mapping between all the possible values of the boolean and the 3-valued enum, and we can use that to convert the data. So here, this task which has complete false gets mapped to status to do, for example. This works quite nicely in the user interface as well. So here I have 2 versions of our issue tracker connected to the same data and running side by side. On the left, I have the one with a checkbox boolean. On the right, I have a dropdown corresponding to the enum. And when I check the box on the left-hand side, you'll see that the dropdown on the right updates to done, which is the corresponding value. And this also works in the other direction. So if I set the dropdown to do or doing, the checkbox gets unchecked. But once I set it to done, the checkbox gets checked. So there is a connection between these data values, even though there's fundamentally different data schemas here. And that leads to an interesting point, which is that this is a lossy conversion. There's information on the right-hand side that's fundamentally not reflected on the left side, and can't be because we only have a checkbox to display. But we think that's okay. The goal here is not to achieve perfect compatibility. The goal is to achieve as much compatibility as we possibly can, given the constraints of these applications. All right, finally, one last example. We started out with each task having a single assignee, and we ended up deciding we wanted to track multiple assignees per task. And to do that, we used a lens operator called wrap, which turns a scalar value into an array. And the semantics there is that the first element of the array should be the value that appears on the scalar side. So once again, we can see how that looks in the user interface. Here I have 2 versions running side by side once again. And on the right-hand side, I'm about to assign multiple people. And when I do that, you'll see that in the right-hand side, I can see those 2 people assigned. On the left-hand side, I can only see the first assignee, because again, that's a limitation of that UI. Hopefully you now have a bit of a sense of what it's like to use Cambria in an application and why it might be helpful. Next, I'll switch gears and talk a bit about some of the key ideas that went into the design of the system itself. So first, how do developers specify these transformations? As we've seen, we build on the theory of lenses, which are a kind of bidirectional transformation first developed by Nate Foster and colleagues in 2007. We directly used a particular kind of lenses called edit lenses, developed by Martin Hoffman and collaborators in 2012. And the idea there is, rather than translating entire states between schemas, we actually just translate edit operations between schemas. And this can have a number of advantages, including efficiency. The rough mental model you can think about is that you declaratively specify some constraints that you would like to hold between 2 data structures. And what the edit lens ensures is that as edits get applied on either end, it translates those edits back and forth so that your desired constraint continues to hold across your data structures. A second question is, how do developers compose these transformations when we're dealing with more than 2 schemas at a time? So in the demo so far, we've been talking about upgrading versions of a single application. And in that context, you could imagine having a stack of lenses that get applied between different versions. But we wanted to support other use cases like diverging branches, so we used a more general data structure of a graph. So we have this graph of lenses, and the way it works is that each vertex in the graph represents a schema corresponding to some version of our application, and each edge between 2 schemas is a lens. So when we have an edit operation in a schema, and we would like to read that edit operation in a different schema, what we can do is pass that operation through the path of lenses to translate it from one schema to another. Another neat thing is that we represented this graph in a serializable way and in a way that could be loaded at runtime, which meant that we had a lot of flexibility in terms of changing schemas without necessarily needing to change the code itself. A third question is, how do we actually store these documents in such a way that they can be read from and written to simultaneously through multiple schemas? We used a structure that we call a version-tagged edit log, and the rough idea is that the document is stored as a log of edit operations, but crucially, every edit is tagged with an identifier for the schema that was used to make that edit. Then when it comes time to read the document, we map over this log and convert each edit operation from the writer schema to our desired reader schema. Then it's just a simple matter of playing for this log, and we retrieve a document that matches our reader schema. This approach has a couple interesting advantages. One is that we can incrementally apply these translations, so as we have new edit operations come in, we don't need to retranslate the entire state. A second advantage is that at write time, we don't necessarily need to know about all the schemas that could exist in the future. So if we created a new schema and added the relevant lenses to our graph, we could still interpret these writes in terms of that new schema later on. And this is particularly useful in a decentralized context. All right, now that I've described the basic design of the system, I'll close by talking a bit about some future challenges that we're interested in. One challenge is that there are certain kinds of transformations which are useful in real applications, but don't fit cleanly into the lens framework because they're not easily made bidirectional. And we're thinking about how we might relax certain constraints in order to accommodate these kinds of transformations. A second problem is that when we're connecting CRDTs with lenses, we need to reason about concurrency semantics and make sure that even under concurrent editing, all the constraints between our data structures continue to be maintained. Finally, I'll close with one more thing, an idea that we call Cambrian software. So in this talk, I've mainly framed this problem in terms of interoperability between versions of the same application, but many of the same issues apply to interoperability between different applications altogether. One of the realities of modern software, especially in the cloud, is that we often have poor interoperability between tools, and one of the main challenges there is that every tool has its own data formats, and it's hard to map between them. And so one thing we hope is that better schema mapping tools like Cambria might help promote a world where people have more flexibility in the tools they use, especially when collaborating with one another. That's it for this talk. If you'd like more details on our work, please go read the paper. Thanks so much, and I look forward to hearing your questions and discussion.